Understanding recurrent neural networks, the power of sequence. Recurrent neural networks, or RNNs, process sequential data with an internal memory. This memory allows them to consider previous information when processing the current input. This makes them well suited for tasks where the order of data points is crucial, like understanding language. Traditional neural networks process each input in isolation, but RNNs maintain a memory of past inputs. This allows them to make more informed decisions based on the entire history of the input. Examples of sequence data include natural language, financial markets, and biological data. RNNs provide a framework for computers to learn from and make predictions about these ordered streams of information. Unlike feed-forward networks, RNNs introduce a feedback mechanism. This loop allows information from previous time steps to be fed back into the network. This recurrent connection is the cornerstone of their ability to learn from sequences. The innovation of RNNs was to incorporate the dimension of time or sequence order into the network's architecture. This enables a more sophisticated form of information processing for a whole new class of problems. RNNs are powerful tools for a wide array of problems involving sequences. The core structure of a recurrent neural network revolves around the concept of a hidden state. This hidden state acts as the network's memory, capturing information from all previous time steps. When the RNN processes an input, it combines this new input with the hidden state from the previous time step. This combination is used to compute the new hidden state and an output for the current time step. The hidden state is a vector of numbers that summarizes the sequential information processed up to a certain point. To visualize how an RNN processes a sequence, we use the concept of unrolling in time. Imagine taking the recurrent loop in the RNN's diagram and laying it out linearly across the sequence's length. This unrolling helps in understanding both the forward pass and the backward pass, known as backpropagation through time, or BPTT. The depth of this unrolled network is equivalent to the length of the input sequence. Despite their ingenuity, basic RNNs face significant challenges when learning from long sequences. One of the most prominent issues is the vanishing gradient problem. In deep networks, gradients can become exceedingly small as they are propagated backward. This halts the learning process for earlier time steps, preventing the network from capturing long-range dependencies. Conversely, RNNs can also suffer from the exploding gradient problem, where gradients become excessively large. Large gradients lead to unstable training, causing the network's parameters to oscillate wildly or diverge. Both vanishing and exploding gradients severely limit the ability of basic RNNs to learn long-term dependencies. These issues drove the development of more sophisticated recurrent architectures. Section 4. Evolving Solutions. The Rise of LSTM and GRU Architectures. To combat gradient problems, advanced architectures like long short-term memory, LSTM, networks were developed. LSTMs remember information for extended periods through a complex internal structure. This includes a cell state that allows information to flow through the sequence with minimal degradation. LSTMs introduce gates that regulate the flow of information into and out of the cell state. These gates allow LSTMs to maintain relevant context over much longer sequences. Another effective architecture is the gated recurrent unit, GRU. GRUs offer a simplified structure while delivering comparable performance to LSTMs. GRUs combine the cell state and hidden state into a single state vector and use fewer gates. The primary advantage of GRUs is their simpler structure, making them computationally more efficient and faster to train. Both LSTMs and GRUs provide a more effective way to control the flow of information and gradients through time. This allows them to handle long sequences and overcome the challenges that crippled earlier recurrent models. Section 5. RNNs in Action Applications, Alternatives, and Enduring Legacy. RNNs, particularly LSTMs and GRUs, have been applied across diverse fields. In natural language processing, they excel in tasks like machine translation and sentiment analysis. RNNs are used in language modeling, predicting the next word in a sequence. Beyond text and speech, RNNs are used in time series forecasting and video analysis. In healthcare, RNNs analyze sequences of patient data to predict disease progression. Despite their successes, RNNs have limitations, leading to the development of newer architectures like transformers. Transformers rely on attention mechanisms, allowing for more parallelization and faster training. While transformers have become dominant, RNNs remain relevant for smaller datasets or specific sequence modeling problems. Their strengths in modeling temporal dynamics ensure their continued study and application in artificial intelligence.